I did put quite a bit of intro in this talk, but I can see there's a very distinguished audience appearing. So please don't get bored. The new Pang told me to do this last year.
Okay, yeah. I mean, anybody have a question, you can just speak out or just put in the chat, and then we'll stop Stephen and ask him. We'll make sure that the students really understand this. Yeah. Okay. Thank you, Stephen. Yeah.
Okay. So this is some work here with my collaborators here. I'd particularly like to mention Meng Zhu, who did most of the work. And there's a preprint on the archive, and the paper looks like it's accepted in Nature Physics now. So as I just said, I was going to give a bit of introduction and motivation for what we're doing. So here's the famous phase diagram of the cuprates. On one, there's lots of different types of order here, which I'm not going to talk about today. The motivation for doing this is to look at things that might affect the low energy properties of the system, things like heat capacity and resistivity. And as many of you know, we see some interesting behavior around this point here, P star, where the pseudogap collapses. We see very strong linear resistivity, and we also see in some systems a rather large specific heat. So in terms of neutron scattering, the things that I think should be relevant to that are the low energy spin fluctuations. So we've revisited them in the overdoped region here, and that's what I'm going to tell you about today. So just to continue in the motivating vein, here's some resistivity from my colleague Nigel Hussey, where he's measured the resistivity here at not at such low temperatures, but he's measured resistivity over quite a wide range here, and he's put fields on in order to be able to see the resistivity where you suppress the superconductivity. And he found this nice plot here, which shows that around about the point where the pseudogap disappears, you have linear behavior in the resistivity, and that comes up on this plot as the red. This is the power law in the resistivity, and then as you go beyond that, you still have this linear part, and he analyzes data in terms of a linear part and a quadratic part, and the quadratic part gets stronger as you continue into the overdoped region here. Okay. Another interesting feature of the overdoped part of the phase diagram in LUSCO is this peak in the specific heat that you get round about 0.22 in this particular plot here. This is some of Louis Taillefer's work where he's collected together different systems, LUSCO and neodymium doped LUSCO and europium doped LUSCO, and he plots the low temperature linear specific heat here, and you can see it's very strongly peaked around this region. So this is an indication, just from general physics, that there should be some low energy excitations associated with this peak. So they could be the spin degrees of freedom that are contributing here. So this is what we're going to look at. So we're particularly going to concentrate on one sample in the region where you get this strong peak. The previous plot I just showed actually involved doping a system with neodymium and europium. So here's some data on the pure LUSCO, and here's some of actual raw data from Japanese group showing the specific heat, and you can see here in the normal state, as we change the doping, going through about 0.19, the P star composition at the linear part of the specific heat increases. So in this particular plot, you have the 0.2 and the 0.22. Here they have the largest value of the specific heat. So there's been quite a bit of work previously. Most papers, I think, ironically concentrate on the superconducting state when they go and measure the spin fluctuations. But I'm going to start out looking at the normal state. A normal state, of course, is interesting for the reasons I've just said. It's where you see the rather unusual behavior of the resistivity and so on. So, so one way to see the specific heat then in the normal state is to go just to TC. And so you can go along this line here and plot out the what the specific heat is, and this is the curve you get. The curve you get here. You can also add some zinc to suppress the superconductivity, and some of these points on this curve are from doing that. Or you can put a very high field on. These open points here are from Klein and Taife's recent paper, where they're measuring very high fields and they get similar points. So this is how the gamma then varies, measured with a number of different probes. Here I've just put for comparison the simplest possible band structure. Well, just an LDA band structure without straight out of the computer, and you can see comparing the two that there's a very strong mass enhancement of the specific heat across this region here. At low doping, these two seem to be very similar, but particularly for overdoped and materials and dopings near this this point where the pseudogap disappears, you get the strong mass enhancement about a factor of 3. Of course, LUSCO isn't the only material that has these large masses. You can see them if you go into the overdoped, really overdoped superconductor here. This is the thallium 2-212. It's a material that's naturally overdoped, and it's a very clean material that you can do de Haas von Alphen measurements in and measure the cyclotron mass for these overdoped compositions. So this would be equivalent to somewhere over here. And there you find, again, quite high masses. So for the de Haas von Alphen mass comes out to be 5.2, and the corresponding specific heat for such a sample is about 7 millijoules. Okay, another thing that may be relevant to this this peak here is the fact that this material goes through a Lifshitz transition in this region, where the Fermi surface changes its topology, and you can see this in some recent data from ZX Chen's group, where they've managed to do accurate measurements of the doping on thin films for the first time, and so they can actually know exactly what the doping is in the RPES measurements, which has been a problem before. And you can see in their data that they see a transition where this point necks off and gives you a Fermi surface centered on gamma at about 0.21, I think it is. So this is slightly below the composition that we're going to be looking at now. Okay, so that's the thrust of some of the motivation. We're going to look to see if we can get an idea what is causing this, whether there's any spin fluctuations connected with this this phenomenon. So a quick look at spin fluctuations in other materials, just to show you that there are already other materials where we see low energy spin fluctuations and at the same time large specific heats. So I've just picked here a couple of some just schematic types of excitations you can get in metals, and I'd like to just show you two examples. One's a condo system actually, and one is a system that may have some nesting strontium ruthenate. And these are the sort of excitations you'd expect. In a condo system, you'd expect excitations that don't really disperse very much. This is a classic one here, say cerium copper 6. You can see here the civic heat measured by Greg Stewart, very high here. The C over T is 700 millijoules per mole Kelvin. That's much higher than the cuprate. So this is heavy fermion values, and it was known at the time. Here's some data, neutron scattering data, showing that there were spin fluctuations with very low energy scales here. So in fact, as you lower the temperature, you can see the energy scale of the spin fluctuations comes down here. And Volta found that it comes down to about half a millivolt. And you can see in this data at the top here, the width across here, the half width across here is about half a millivolt. So this is very low energy fluctuations. This shaded in here is the magnetic scattering. This is the incoherent scattering we see with neutrons from the nuclei fluctuating. So you have to ignore that. And as you change the temperature, this shaded area gets broader. Okay, so that's one example. So the energy scale of these fluctuations is very low. It's going to be, this is lower than we see in the cuprate. So I'll show you later. The other material.
Steve, can I interrupt you?
Please ask.
Yes, Steve. I guess it's a tangential point to what they are making, but what you were showing are the high temperature behavior for the heavy fermion systems.
Yeah. What's your question, Jim? Now?
Yeah. Well, I mean, these temperatures are above the Kondo temperature for cerium copper 6, right?
Yeah.
So at the low temperatures, in fact, peaks in the Q space develop.
Yes.
Peaks away from Q equals 0.
Yes. I'm just giving a sort of broad picture of it, that there are very low energy excitations. So one has to sort of average over everything.
Yeah.
But yeah. Yes. Oh, yeah. Okay. You're saying that my picture here isn't quite good enough.
Yeah. If I go below the Kondo temperature, then structures develop in the Q space.
Yes. Yeah.
Yeah.
Okay. This material, so the strontium ruthenate, of course, has a lot more structure, and we see that we can actually correlate the changes in the spin fluctuations with changes in gamma in this material. So if we go to this point here, for example, and change magnetic field, you can see the energy scale of the spin fluctuations changes. Here it goes down to actually lower energy scales than I showed in the previous example. Goes down to about 70 micro eV, but only over a small range of reciprocal space. And in this material, we see that this is the specific heat on the right hand side. This line here, it changes and it has a peak where the energy scale of the spin fluctuations is lowest. That's this panel D. So there's two examples where you get low energy spin fluctuations and large gammas. Okay, so let me talk a little bit about the cuprates first. So I may cut some of this short, but I thought, as Peng-Chen was saying in the introduction, there's less people working on cuprates and maybe some new people. So I thought it might just be worth saying a little bit about spin fluctuations in general and cuprates, and how what I'm going to show you connects to the rest of everything. So I've added the cuprates to my zoology of spin fluctuations. So actually cuprates, the parent compounds are antiferromagnets. So they have a dispersion like this, and with strongest spin fluctuations near the ordering vector of the antiferromagnet. And then as you dope them, this stuff spreads out, broadens, and actually at low energies here, near the where it orders near pi pi, for the superconducting materials, you get the famous 4 peaks. I've illustrated this here. This is a cut through reciprocal space, and then the scattering is peaked away from the or what was the ordering vector of the material. And the two probes that people use now to measure the dispersion of spin excitations, right, are RIX and inelastic neutron scattering. So RIX is a lovely probe, but it can only reach up to it can't reach actually to pi pi in the cuprates because of the energy of the X-rays that are used on the copper resonance. So you can get this part of the spin fluctuation really well. On neutrons, you can get the whole thing, but you have problems with having very big samples and so on. So I'll just quickly show you where we are with RIX and neutrons, and then move on to the rest. So I'm going to show you a bit about the parent compound, and then a little bit about what happens with the dope compounds. So quickly, the parent compound is an antiferromagnet. Here's some of our work on the parent compound. You can see dispersive the antiferromagnetic excitations here. They fall apart at a particular point in reciprocal space, the half-a-half, and they're different along different directions along the say along the pi pi or pi 0 directions, or half-a-half or half-0 direction. So you have some dispersion between the different directions. Here's the falling apart of the magnons, sort of spin-on decay, we call it, at this particular point here, the half-0. The magnon is broadened and has a much higher lifetime, and this behavior seems to persist into the superconducting compositions. So here you can see the difference in the zone boundary magnon energy between these 2 points. It's higher at this point than this point. Okay, I'm mentioning that because now you can see that quite clearly in much of the RIX data, and it actually fits in with what we see with neutrons for the dope materials. So here's some RIX data, and you can see the 3 compositions here. So this is the parent antiferromagnet, this top one. This is a doped 0.21 and then 0.26, and you can see the RIX can access this region here. So we can go along this line, which is this one here. Okay, and that's the higher energy direction. And then if we go along here towards pi pi, you can see the magnon doesn't come up so high. And then if you dope, you can see the whole of this thing is broadened out and it drops in energy, but you still have this anisotropy as well. This is a higher here along the H0 than along the HH.
So Stephen, what's the reason for the magnon to have a very strong damping even in the parent compound, where it's a strong the magnon interaction, or what's the reason for that?
You mean this one here?
Yeah. In the parent compound, and where it's supposed to be insulated, right? Typically, insulator is extremely hard to have a damping of magnons, right?
Well, this is something that occurs actually it's particularly here. It occurs in all spin-a-half antiferromagnets, and it's something that and it's been seen in ones with much lower J's as well. And it's believed that the magnons are sort of unstable with respect to some. They unbind and you get spin-ons.
I see. So for spin 1 and other systems, I mean, does this happen or doesn't happen at all?
In spin 1, there's some it doesn't the magnons are the magnons don't have this they don't behave like this, no, but there may be some dispersion residual effects that you some smaller effects you see on the dispersion in lanthanum and nickel oxide, for example.
Has this effect been accounted for by theory? I mean, as you know of, or anybody know of?
Well, that's more a question for Sabir and people.
Actually, yeah, so Stephen, this is Bruce Golan. I thought the original interpretation of the inelastic neutron data it was a paper that predates this one by Coldet et al. Was that weak dispersion was due to ring exchange. So it was due to a detail of the Hamiltonian. Is that not correct?
That is correct, Bruce, yeah. No, I think there's two things going on there. There's this difference in the dispersion along two directions, which, as you say, can be interpreted as ring exchange or longer range hopping. But the fact that the magnons are unstable in some particular parts is something else.
Okay.
Okay. Yeah. So. Okay. So that's. Is there any more questions on that? I'll just.
Yeah, Subir, do you have any comment?
No, I think what Stephen said is fine. It's understanding of language is much harder. Yeah.
Okay.
And there are proposals that has to do with spin-ons. Yeah.
Okay, thank you.
Yeah. So this interestingly, this difference here, you see this as the point that Bruce made, but coming from the here is persisting into the superconducting compositions as well, and we can see this is now neutron scattering. So this is some older data. You see this is now cutting constant energy cuts for superconducting composition, so 0.16. So at low energies, you can see the 4 peaks, and then you come up, and at higher energies, you see this thing that I just showed you. This stuff here. Say this point here would be at going along the HH direction, and this is this energy of about 150 millivolts. So this would be, well, here we've got 150 and 130 here. So this thing here, these things coming in along this line, and you can see it comes along here and here and here. This is that's that branch that I showed you in the RICS. So it's very nice that the RICS gets to see this stuff, and then when you go to a half, you see this big with what's left of the spin wave coming out of here, I guess, is very strong, and this is what you can see with the neutrons. So it kind of links up. I think it's linking up now the two probes. Okay, so we have a good picture of the whole of the scattering at higher energies. So one thing one can do with neutrons is to integrate everything up over the whole Brillouin zone, just to get a sort of a bigger picture of what's happening, and this is what you see here. So in the parent compound, this is the so-called local susceptibility, where we just integrate chi double prime over the whole Brillouin zone and get like a density of states for the magnons or whatever. And this is what you get. Of course, this would carry on up to 300 millivolts and start to go up. Okay, and then as we dope, we get this peak developing here, which is around pi, and then this disappears as you go to overdoping, and then the incommensurate peaks that I showed you down here. You see they come and actually they go away at about 25 in this case, and that gives you, when you integrate this up, you get this this peak here, for example. This is due to this low lower energy part from the incommensurate peaks. Okay, so this is going through now different compositions to the overdoped one, which I'm going to talk about. So what I want to talk about today is what happens at the lower energies here. Now, unfortunately, so when we did all these experiments, actually they're done with relatively poor resolution, but they're also done in the superconducting state. So this peak here and this peak here are partly resonance peaks. You shift spectral weight up when you go into the superconducting state. But you can see, as you'd expect, that as the gap drops and so on, that this goes down here. Okay.
So Stephen, I have another question. So when you sum up the total spectral weight as you go from 0 to 0.22, I mean, from neutron perspective, you can clearly see a reduction of the total spectral weight, right? I remember that the X-ray people saying, that's not true, right? I mean, is there any reconciliation on this point?
Yeah, that's a very good question. So I think that probably the X-ray people, well, I have my foot in that camp as well. This is from the X-ray people, right? And you can see that statement is not quite true. There's huge changes at high energies in this particular plot. Here, this is taken on the same spectrometer with different samples in the same configuration. And you can see this is very different to this. It broadens out and so on. So to say that there's not, I think some of the early experiments, maybe there was a strong statement, but there are definitely changes even in the X-rays at high energies. Of course, the truth is sort of somewhere in between. There's the neutrons see a rather extreme change because they're not measuring the same place, right? This is measuring the Broglie zone boundary here, and neutrons are measuring in the center here near pi, where the biggest changes occur. So in terms of the spectral weight, I don't think there's a problem in probably this. The problem more is that maybe we haven't, well, we may not have captured everything here, but I think that there's the higher energies where there's things are not dispersing very much, the neutrons maybe not be picking up some of the weight, because you have to look at to have contrast to see the signal in neutrons, whereas X-rays you can directly see it. Yeah, so this part up here probably is underestimated with the neutrons. That is true. But this part here at the low energies, I think, is clearly changing with the neutrons. Okay, that was kind of my introduction then. I basically wanted to finish up with saying that, we're measuring the tail, if you like, that wags the dog. So there's a lot of spectral weight at higher energies, but this low energy part, which I'm going to talk about, is nevertheless interesting, I think. Okay, so let's go on to the low energy stuff. So just before we talk about the neutron scattering, I wanted to go to sort of really low energies and talk about and put our work in context with this this stuff done by Marc-Henri Julien, for example, where he's measured the spin freezing. So you can see this here. So this is spin freezing, of course, or spin glass, as he calls it. And you can see that there's something going on centered around 1/8 or 0.12, where you get incommensurate structures when you measure it with neutrons, and you can see with the freezing occurring when he measures it with NMR. So you can see things slowing down. But he can also do a rather nice thing and put a larger magnetic field on, suppress the superconductivity, and he sees that this increases this spin ordering at low energies, at low frequencies. So and he can see that when you put a field on, it persists up to a much higher doping, up to P star. is his claim. So we have got this very low energy stuff there existing, but disappearing at about here. So we're going to be measuring in the new sample I show you today over here, where this thing is gone.
Steve, can I ask whether this is only for LISCO or whether other cuprates also show this?
Good question, Kim. Yeah, I don't know. The answer to that may come to me later on, but I don't know if similar measurements have been done on other things, but maybe someone can correct me. Not with field, but this freezing phenomenon occurs in other cuprates. Yeah, so the zero field part does. Yeah.
So something like YBCO also shows this?
Oh, no. YBCO, yeah, in YBC, this, yeah. That's a good question. Yeah, this does not occur in YBCO in the same way, except perhaps at much lower dopings.
Okay.
And one might ask why that is. And I think my personal view is it's probably connected to the charge order and the structure of the materials. Right.
Thank you, Steve.
Does that? Yeah. Okay. So this is some of actually Bruce's work here, where he's looked at neodymium doped, and I just want to emphasize neodymium is different to LUSCO in that it has this region of order that persists over a much bigger range, up to 0.1, up to 0.26 or somewhere up there, and you can see this is measured here. So this is now people often show the neodymium doped and the LUSCO in the same thing, but it is different, that this spin order parallel spin stripes, as Bruce has called it, exists up to higher doping here. So okay, so big difference. Right, so now onto what we've been doing. So I just a bit more history actually. Here's some. We're going to look at the sample here, sample 3 at 0.22. As Tomo was saying earlier on, there's some old work from Bob Bergeno and Wakamoto, who looked up here. I'll just mention that. And there's some work with me and Gabe down here at sample 1, which is 0.114. And there's some work with Gabe and Bella Lake. And they've measured here. So these are all materials these are all compositions where people had a good look at the low energy spin fluctuations. So I'll just mention the Wakamoto paper here. So this is this we're really following on from this work. So this is a summary of what was observed if you go to the very high dopings here, so 0.25 and 0.27. Example that you see in commensurate peaks. You see a peak in the scattering at about 6 millivolts. This peak doesn't change when you go into the superconducting state. There's only one line here. This second line down here is for another composition. So as you can see, the statistics are not so good. You'll see that the data we have actually is different to this qualitatively, but this is identifying that there is scattering there. Okay, so now that was a sample here. I'm going to just quickly show you this recap on the paper we did here, because this is this sample number 1 with that we did a while ago with Gabe. Covered the same energy range, and it's a good comparison with what I'm going to show you today, our new stuff. So then now this is a sample of 0.14. Okay, so it's a sample that is in the pseudogap part of the phase diagram, but it's sort of it's not affected by the spin freezing because we're at higher doping and higher temperature. So what we saw is that if one goes to one of the incommensurate peaks and plots the spectrum as a function of different temperatures, this is what you see. You see that the susceptibility increases below the temperature. And at the lowest temperatures, the energy scale that we come out with is about 10 millivolts. that's the peak in this fit here, this Lorentzian. And then we were able to do some scaling here, and this is scaling the width of the excitations for different energies, kappa, against this plot here, and you can see we got some scaling. But the interesting thing is that we didn't see a divergence in the correlation length, and we didn't see the divergence in the energy scale either, or energy scale going to 0. So it seemed to be heading to this point here. And at the time, I think we concluded that that was just because we were not actually at the sort of quantum critical point, as it were. But I think maybe a more likely explanation now is, in view of our new data, is actually this is not maybe really, this is the pseudogap is setting this energy here. Of course, it's hard to distinguish between a pseudogap and a something that sort of just drops down at low energy. But this energy scale is going to be much larger than the one that we find when we go to the overdoped side. So I've just put here provocatively, the divergence is limited by the pseudogap. And here's the parameters we got in those days then. So this is this here, and this was the inverse correlation length. Okay, so the inverse correlation length is coming from the width of the peaks then here, and this is coming from this. Okay, so the new data then we're going to collect on a sample. In order to do the stuff on the lowest energies, we had to have 30 grams of sample. We used 3 spectrometers. So 2 of them are at ISIS then, and we have lots of detectors. And you can see Rob Bruley here standing next to these very long detectors, which we used. We used Merlin as well, and then iron 12 at the RLL. And we use lots of different energies in order to get to see the low energy excitations, in order to understand where the phonons were and so on. And we've also put 8.8 and 10 Tesla on. Okay, so the first thing we did was to check whether we had any spin freezing in our sample. And this is on iron 12 now. We're scanning through one of the incommensurate peaks where we would see the spin freezing. Okay, and this, I've put this dotted line here just to show you the width of the peak that would expect. This is the resolution, and you can see there's nothing. Well, there's one can fit a peak. The biggest peak you can fit is about 0.006 Bohr magnetons per copper atom. Okay, so it's very small. And just as a reality check, we also measured a sample where we'd expect to see a signal. So it's a more lower doping and in a magnetic field. And here is that measured in 10 Tesla actually. That's what you would expect to see if there was some spin freezing. So and this we can work out by normalizing the intensity that this corresponds to a moment of about 0.03 Bohr magnetons, right? So our sample is not, what we're seeing, and I'm going to show you, is not due to any order or excitations of that order. Okay, I put here the 2 samples actually. This is our sample that we're measuring now, and this is the sample that this one with the peak, so it's somewhere in here.
This is elastic scattering?
This is elastic scattering, yeah. Or lack of elastic scattering. This is elastic scattering, this one, yeah. Thank you, I should have put that on.
And Stephen, are those both in 10 Tesla?
No, yes, they are. Yes, they are, sorry, Bruce.
Oh, did you also look at 0 Tesla for the 0.22?
Yes.
And is it also has no Bragg scattering, I guess, is that right?
That's right, yeah.
Okay. Yeah, thanks.
Okay, so there's okay, so that was a bit of bookkeeping for the to make sure that we were measuring a sample that is not ordered, what we expected doing. The other thing we did is measuring these spin excitations is one of the problems is that there are phonons as well, obviously, in the material. So we've got to make sure that what we're measuring is not a phonon. So here what we see is some data where we're going through the peaks. This is now an LET along this dotted line here. And you can see this is the magnetic scattering here at low energies. So 2, 3, 4 millivolts. These rods are these going through here. And this is measured actually with as small a Q as we can. So we go in the first Brillouin zone to try and remove as much phonon scattering as we can, because in general phonons, the cross-section of phonons would go as Q squared times some structure factor as well. But so you want to get Q as low as possible, and so of course you have to go into the first here. Actually, it's lower. There's lower. You can see there is slightly lower background here than here because there's a little bit, but you want to make sure that it's as small as possible. And then you have the third dimension along C direction, which you'd like to integrate along to get intensity. So we limit that to this range here, -1 to 1 along the C star direction. If we go out and do the same in-plane momentum and increase L, for example, and go and have a look at the around L equals 4, which should be the same. Here you can see this. This is what the phonon that you would expect that you see. This is a phonon. This is a nasty phonon sitting there at about 7 millivolts, which is not present in our data here. So
is this optical mode or acoustic mode?
It's an optical mode, yeah.
Okay.
It's a mode that actually Bob Bergeneau found it's a mode that does things when you go through the LTT nodes. So from the high temperature tetragonal to the low temperature orthorhombic transition, it moves around and things. It's yeah. So it's an optical mode. Okay, so right. So now here's some of our data. So what do we see here? We see cuts through the low energy scattering. So first of all, if I just start on the right-hand side here, so this is in the normal state, which we're most interested in here, 26K, so it's just about TC in zero field. So we see at the lowest energies, so we can go to very low energies here, 1.2 millivolts. You can see very nice peaks there. And as we go up in energy, 5 millivolts, they can still see them, and then you can see they're starting to broaden here at 7.5 millivolts. Okay, and then if we cool down into the superconducting state now, you can see these things disappear at the lowest energies, and they actually get a bit stronger. You can see there's a bit more red here, there. And then if we put a magnetic field on and cool down, again we see these peaks here. So this is raw data, so we haven't corrected for the Bose factor. So I'll come to that in a minute. So, and then if we look at the raw data, just to show you what the raw data looks like, you can see again, here's the 1.5 millivolts, sorry, 1.25 millivolts at zero, at high temperature and 0 Tesla, and then we go into the superconducting state, and now it disappears into these blue things. Okay, so that was really just to show what the actual data looks like if you don't plot it as a color plot. Okay, so the most important plot, I think, of the talk then is this next one. So what we're going to do is to go and look at this point here, and then just plot the raw data as a function of, or plot it as a function of energy. And so we take this point here. Actually, we took all 4 points and added them up, and then just to get a spectrum at this point here. And this is what we find then. if we go to Q delta, as we call it, the incommensurate point. So we see in the normal state then that the energy scale here is about 4 millivolts, and this is lower than we had when we were at lower doping. So now in the overdoped region, the phase diagram, we're finding lower energy scales than we found in the below the Pseudogap doping. So
the wave vector is the same.
The wave vector is this one here. Yeah. Oh, the wave vector has changed slightly, of course. Yeah. This has moved a little bit. I'll show you the comparison of that in a second, and I'll have a table with all the parameters. So we're sitting on the top of the peak, and then what we find is that the energy scale has dropped down to about 4.6 millivolts. Oh, it's written here actually, compared with 9.6 for the other sample, which is well studied. Okay. So this means there's a low energy scale in the normal state. And interestingly, the energy scale is about 2 times the temperature. If the temperature is 26K and the energy scale is that, so sort of Planckian, I guess, but within a factor 2. Okay, and now we've got our other data sets then just compared. So this is the one I just showed you, the normal state. So I think maybe first, the next most interesting maybe is the mixed state. So now we're going to cool down to 2K and we can only get 8.8 Tesla on this particular instrument, so rather than 10. So this is the mixed state here. This line here is this one here. So just for comparison, so you can see in the mixed state now at low temperatures that everywhere the scattering has become stronger. Guidable prime. So I've taken out converted the data to get the susceptibility here, taken out the Bose factor, and it's stronger everywhere. And then if you think about it, because it's the mixed state, we could think of it as superposition of a superconducting part and a normal part, if you like. So the superconducting part, if I just come back to this in a minute, but let's now take the field off, and we see what the superconducting part looks like. So there's a suppression. There's a suppression of the response at low frequency, as you'd expect, and then an increase here at up here. So this increase is the so-called resonance, right, that we're seeing. So the superconducting part looks like that. So then back to the mixed state, if it's mixed and some of it looks like this, then there must be some bits that actually have an even lower energy scale than is shown here. So that's a bit surprising. This one fits almost exactly a Lorentzian. Well, this is Lorentzian. Unfortunately, this is obviously going to be more complicated. Okay, so the mixed state shows even lower energy scale, and the superconducting state shows the old magnetic resonance excitation. So I've just introduced, just schematically, what seems to be happening then is that, so if we imagine in zero field, we start off, we sample somewhere here, and this color is supposed to represent the strength of the low energy spin fluctuations. So the ones down here, say, for the sake of argument, say one's at 1 millivolt. So we see some spin fluctuations in the normal state. If we drop down in temperature, they're suppressed by the superconductivity here. And then if we put a field on, we bring back the fluctuations, and maybe even more than we had before. So I've just made the sort of ideal case that we can put enough field to go back into the normal state here. And then it seems that then we would then get more spin fluctuations so this is the basic picture. And then as we go as a function of doping, then it seems that the low energy spin fluctuations seem to get stronger, and I've tried to illustrate that here. Okay, so now back to specific heat for a minute. Here's some data from Klein and Taifer. So this is the sample we looked at. Well, the same composition, at least. Peak was 0.22. So you can see they've gone up to 40 Tesla here, and then you can see that the gamma increases rapidly as you getting new low energy excitations as you put the field on, as you'd expect. Okay, so finally, how long have I? Peng Chen, how much longer do I have?
You can go another like 10 minutes, 5 to 10 minutes.
Okay. Yeah, that's fine. That'll do. Yeah. All right. So okay, so we've seen that. So now a bit of fitting of data and so on. Parameterization of the data. So the data fits pretty well to we're able to do pretty good global fit to this cross section here, which is this is the Minis-Monian Pimes type cross section. We use a similar one in this Apley paper here. Just modified, of course, to give the 4 peaks. You have to use this R function, which is proposed by Sato and Maki, and it's this function here. So this is the function that gives you the 4 peaks, and it has the property, which I haven't written here, that as you come away from one of the peaks, this function goes as sort of q minus q delta squared. So it goes as little q squared. So it looks like a normal sort of Minis-Monian and Pimes type thing. It's a small q. So that means that the prefactor here you can interpret as a sort of correlation length. Anyway, so you can fit the whole thing basically with this, which has got various parameters. So it's got an overall susceptibility, it's got a correlation length here, and it's got the energy scale at the delta position here. And then you can take the imaginary part of that, and that's this thing here. That's the thing, of course, we actually fit. Or you can sort of interpret this just then at any point in reciprocal space, we've got this extremely overdamped oscillator that's a Lorentzian. Okay, so if you go to the extreme damping limit of damped harmonic oscillator, it has this form, and then the line width, the characteristic energy of this varies like this. So we can fit these with these 4 parameters: real bar susceptibility, correlation length, incommensurability parameter, and the relaxation rate. And so here's the fit here. On the right hand side, and this is the data. So of course we fitted a lot more data than is shown here. And here the parameters we had compared to the underdoped sample, a slightly underdoped sample, and this is an overdoped sample. So you can see that the energy scale has dropped, and the correlation length has actually decreased. So the inverse correlation length has increased. I've plotted the inverse correlation length here to confuse you. So the energy scale drops, and normally when the energy scale dropped, you would say, the correlation length is going to increase if we're going to some quantum critical point, but it hasn't. It's gone the opposite way. So if we just look at how things might scale if we were to just stay at low temperature, or and this does not, you're not going to get any scaling. So it's not these, of course, we only have 2 points, but it means that something else is going on, I think. And as Sabir asked if delta changed, so delta changes a little bit, but we've moved. Okay. The other interesting thing, as Peng Chen said earlier on, that you can put things in absolute units. So we can work out what the fluctuating moment is for this piece of the cross section that we fitted with the function I just showed you. And these are the numbers that come out here. So we find it's the moment squared is 0.19 for magneton squared. Okay, obviously when you're doing elastic scattering and you sum it up, you get the moment squared. So a key point I think of this work is that this is hugely bigger than the stuff that Mark and Resurgent was looking at, the spin freezing. So those moments are about 0.03. If you square that, you get 0.309. So this scattering I'm showing you is orders of magnitude bigger than the freezing that is seen. So finally, a bit of Longzerich-esque work. So spin fluctuation heat capacity model. Okay, so what we've done is to just try and the simple theory here, which is the Paramangnal theory, basically estimate what the specific heat would be for these overdamped excitations. Okay, so this is an expression for the free energy when you have specific heat, which is arising from the virtual scattering of electrons off the Fermi surface via spin fluctuations, are proposed, well, in these old papers here, but Gil Longzerich wrote it down as explicit form here in this paper, and it's also in a paper from Maria and collaborator here. So this is the free energy. So basically, what we need to put into this expression is this gamma from the relaxation rate of the spin fluctuations. So the RPA theory sort of calculates this, and basically we're inserting the experimental value into this. So helping the theory by putting in the RP susceptibility, interpreting our data as the RPA susceptibility, put it in here, and that gives you the free energy in this expression, where this thing here is the free energy of a harmonic oscillator. So you can use this to evaluate the heat capacity. So I don't have to tell this audience that what we're doing is renormalizing the quasar particles and so on. And I wanted to emphasize that these renormalizations may actually only be over a very small energy range from the thing that we're seeing in our data here. An energy range of order 5 or 10 millivolts. Okay, so you can use that expression to get the specific heat by differentiating it twice and doing and so on, and you get this expression here. And you can either evaluate this analytically at finite temperature, or you can use this low temperature limit here. So we know this from our fit, and one sort of thing is this cutoff, which has to be there because of the nature of the cross section we used. Anyway, if we do it as a function of cutoff, you can see that it converges to a value. And these are the parameters that we found in our fits. So we put them in here, and we can work out a value for the specific heat using this. And it comes to about 16 millijoules per mole. So the interesting thing about this plot here is if we do this as a function of cutoff, we can see that the fluctuations that we've measured up to about 10 millivolts are actually the ones that are causing the specific heat in this model. It's not like we're extrapolating up to 50 millivolts or something. So in this model, fluctuations we measure account for most of the gamma. Okay, so here we are. We can do this actually for two samples. Then the one we're measuring, the overdoped one here. This is the number that comes out of that calculation, and the measured specific heat is 14 here. And then this is the one that's slightly underdoped, where the energy scale is higher, and so we'd expect specific heat to be lower. And this also sort of agrees. Yeah. So here's the specific heat values put on top of the measured curve. So in summary, we've observed very low energy spin fluctuations, a normal state of an overdoped superconductor, very low being 4.6 millivolts. Of course, that's not as low as heavy fermions and so on. But this if I jump to this one here, this energy scale is comparable with temperature, so it works out as about 2 kBT. Obviously, it's going to increase as we warm up. In the mixed state, then the energy scale becomes even lower, as you can see here, and the susceptibility or Kaiser prime at low energies becomes larger. So the spin fluctuations we see, presumably, they're associated with the collapse of the pseudogap. And we can account for within this model I showed you, we can account for specific heat, at least, and its variation with doping between these 2 points, which are obviously to each of these points is several weeks of beam time. Unfortunately, it'd be nice to have lots of points, but that's the way it is. Okay, so thank you for your attention.
Thank you very much, Stephen. Yeah, very nice talk. Yeah, questions? Well, maybe I can ask you, since I'm have a microphone on. Yeah, so basically what you're saying is that as you increase doping, the total magnetic scattering decreases, but your changes of the magnetic scattering actually increases, right? That which contribute more to the heat capacity, right? Is that the central claim?
Yes, the total scattering. Because
the total magnetic scattering is decreasing, right? But the changes of the magnetic scattering, because of the contributing to heat capacity is actually increasing as you go from underdoped to overdoped side.
That's right. The total. I'm a bit uncomfortable with the total magnetic scattering. I mean, we've just measured. What we found is that there's a piece of scattering, as it were, at low energies. It's on the tail of something else. Obviously, there's a sum rule, and the others. There's other stuff's incoherent stuff in other places in reciprocal space and energies. But this coherent fluctuations that are giving these 4 peaks, they've got weaker, but they've gone down to lower energies. Okay. And you can quantify the weakness. I mean, there's 2 numbers, right? I've integrated this. This is just summing up when we fit over reciprocal space and the energies, because it's going to drop off, as you go to higher energy, this particular form. So that's but you can see you can convert it to a susceptibility as well, and that also has dropped.
Right.
Yeah.
Okay, thank you. Yeah, Subir.
Yeah, related question. I think you showed some data earlier. Could you remind me what happens to the spin spectral weight at 1/2 as a function of doping?
You mean this one, or?
Yeah, I believe so. So the blue region is all at 1/2, peaked at 1/2. Is that right?
No, this is integrated. This is basically an integral over this.
Right, but what's happening at pi? There's a resonance mode or something. There's a gap excitation there, right? Or does it disappear or no?
What's actually happening at a 1/2? You mean if I was to make this plot at a 1/2?
Yes.
What would I see?
Yes.
Well, I can tell you what, Sabir, I can tell you what we wouldn't see. We wouldn't see a resonance mode because the resonance mode seems to occur at the incommensurate position. So if one was exactly at a 1/2 and came up through this hole in the middle, then you would wipe out this thing completely.
Okay.
Right, because this feature is due to those 4, these 4 peaks, right, which are slightly away from 1/2, and then this thing here seems to appear. You can see here at 41 millivolts. The first time we see it is at a 1/2.
Right.
And at 50 millivolts here it's strongest, and then it seems to disperse out.
I see. So it's what doping was that?
This is optimally doped. so it's 0.16. Yeah, here.
Okay. Oh, and this, so what's being changed in these different pictures? These are different energies, right?
Yeah, sorry, these are just slices of different energies. So this is 10, 18. Yeah. So this is like slicing slicing it at different energies. Yeah.
Okay, thank you.
Chimiao?
Yes, Steve. So I was trying to sort of think about this two dopings you have, and the statement that if you look at the width, it seems to be the opposite of what one would expect to see if there were a quantum critical point near closer to 22%, and yet your specific heat analysis seems to have the right trend that's increasing as doping changes towards 22%. And so I wonder, maybe you said this, how many temperatures do you have at your doping?
How many temperatures do we have at
in the measurements?
We have 2 temperatures in our measurement.
And the width, the peak is sharpening as temperature is lowered. Is that correct, or is it?
No.
Yeah. So here's the all our data collected together. So 0.22. So I didn't really speak about this, but you can see that as the temperature is lowered,
More or less the same.
sorry, there's something missing here, isn't there?
No, you should look at the 4th column, right? 5th column, 6th column, yeah.
The
Gamma,
six-
inverse gamma, right? It's almost the same, 0.053 and then 0.057, right? The correlation is the same, right?
Yeah, sorry, yeah. Yes. So the correlation length, when we put the field on, as you said, is unchanged, is basically the same. Yeah.
I see.
Yeah.
But nonetheless, the damping rate that you extract is changing a lot, and it's decreasing as temperature is lowered. Is that correct?
Yeah, but well, I've put a blank here because we put a blank here because this damping rate here is defined by fitting a this Lorentzian form,
Okay.
which you can do. It fitted very well for the Apley plot and this data, but of course in the mixed state here we have this thing, yeah, and it's not going to be a homogeneous system, so it's hard to say what to say, but I guess it has to be lower, doesn't it, for the normal bit, because this is all, yeah.
I see. So I suppose it would be easier to think about it if there were 2 temperatures both in a normal state.
So again, if there's,
I'm just trying to see whether this the statement that the damping rate goes like 2 twice of kBT.
Yeah.
Of
Well,
H bar.
Yeah. So this is another experiment that we want to do. I mean, because each of these things takes basically takes like 2 days, so we have 6 days or whatever. So yeah, so by going into superconducting state, you're making things more complicated for yourself, right? Yeah. What you want to do is to go upwards in temperature from and look at the normal state, so double the temperature or something. Yeah. So we have not done that.
Okay.
Yeah.
Thank you, Steve.
Okay, any other questions for Stephen? Great. I mean, yeah. Okay. Yeah. Thank you so much, Stephen. Yeah, this is fantastic. I mean, yeah, this result really particularly interesting because you actually connect, sort of a spectroscopy with the thermodynamics measurement. That's not easy to do. and without basically with no parameter, right? Yeah. Very nice result. Yeah.
Mhm.
Yeah. Thank you.
Okay, well, thank you all for coming.
Stephen.
Sorry?
Jeff says thank you.
Yeah. Bye-bye. Yeah.
Yeah, thank you, Steve. Good to see you.
Yeah.
Yeah. Good
Okay.
seeing you. Yeah. Okay.
Good to see
Bye.
you
Yeah, very nice talk.
Thanks.
Yeah.
Bye.
Bye.